Hi, ladies and gentlemen. We're going to be talking about atomic radius and ionization energy today. And this is a continuation with what we talked about in class today, and some of it will be a review of what we talked about in class. Other of the stuff is going to be, some of the stuff is going to be new. So just a reminder here, and we're talking about atomic radius, that distance from our nucleus to our outside electrons, or we could say it's half the distance between the two atoms that are bonded together, is our atomic radius is going to increase as we go down a group. Now, we need to know the reasoning behind this, not just the group trend. And so the reasoning behind this is because as you add more electrons into greater energy levels, those electrons are going to be further away from the nucleus. So we say the principal quantum number n is increasing. So let's say we take our alkali metals going from lithium to sodium, potassium, rubidium. We're adding electrons into the 2s orbital, 3s orbital, 4s orbital, 5s orbital. Those electrons that are on the outside are getting further and further away from nucleus. Then you're also adding in all those other 2p, 3p, 4p orbitals and all that stuff. That is causing that atomic radius to get bigger. And we know that as we go from left to right across a period, we're going to see a decrease in our atomic radius, and this is basically due to our increasing nuclear charge. And what does increasing nuclear charge mean? Well, it just means we're adding more protons. The electrons are being added to the same energy level, so the atom is not getting any bigger, but more protons pulls those atoms in tighter. Okay, and we talked about that in class. And so let's kind of scroll down here and talk a little bit about parent atoms versus ions. And what we mean by the comment, or what parent atom means, is just any atom in its neutral state, like let's say calcium or I don't know, bromine would be considered a parent atom, whereas the ions of these would be the calcium ion, which is Ca2+, or the bromide ion, which is Br1-. And so we're looking at size here in metals versus cations. And so we'll start with that. So let's say we'll use this calcium example. If we have a neutral calcium versus, let's say, a calcium ion, which one is going to be larger, which one's going to be smaller? Now we have to remember, when a calcium ion is formed, we have 2 electrons which are lost. And those 2 electrons lost gives us a 2+ charge. And so what's going to happen here is when we look at size, and if you've lost 2 electrons, that's going to make you a little bit smaller than if you have all of your electrons. So metal ions in general are bigger than their cations that they form. Over here on the non-metal version, nonmetals versus anions, let's take that example of bromide. So if we do bromine versus the bromide ion, we have to remember that the bromide ion, we have gained 1 electron. It has 1 more electron than bromine, so bromine has just 35 electrons, where bromide has 36 electrons. So we're going to say that bromide is going to have a greater mass, or a greater atomic radius than bromine, which has 1 less electron. So we need to know how to explain that and why that occurs as well. Next thing I want to talk about real quickly here is what is called an isoelectronic series. Isoelectronic series are essentially just a group of ions that have the same number of electrons. So let's just pick one here. Let's say we have neon. Neon, a neutral atom of neon, is going to have 10 electrons. Well, there's a lot of other atoms that can also have 10 electrons. We could have the fluoride ion, which normally has 9 electrons, but in the ion form it's gained 1 electron, so that's going to have also 10 electrons. We could have oxide, which normally oxygen has 8 electrons, but it's gained 2 electrons, now it's got 10. We could have nitride. And then on the other side of the periodic table, we have the sodium atom, which normally has 11 electrons, and so it is lost 1 to gain a 1+ charge. Now we could have the magnesium atom, which has lost 2 to gain a 2+ charge. So we would say that all of these atoms in this series are isoelectronic with each other because they all have 10 electrons. Okay? Now, down here we're giving you a sample test question, and then we want to list from small to large with respect to atomic radius. So just one thing to remember, if we're looking at the periodic table, atomic radius is going to increase down, and it's going to decrease to the right. So we're being asked to figure out who is the biggest and the smallest for magnesium, calcium, and the calcium atom. So magnesium resides right here, and calcium resides right below it. So first off, we know that calcium is going to be the larger of the two. Now, when it comes to the ion, we're looking at the calcium ion versus the calcium atom versus the calcium ion, and the calcium ion has lost 2 electrons, and so that's going to make calcium the largest. And then, oops, I just made that the wrong way. Calcium is going to be our largest, where our calcium ion is going to be the next largest, with magnesium being the smallest of all of them. And actually I just listed them large to big, and they wanted small to large. So hey, let's just change the question and make it large to small. There we go. Makes it right. Okay, same thing over here for apparently the second part of A, which should be B. That's a typo. Let's make it B. And again, we're dealing with sulfur, the sulfide ion and the oxide ion. And remember over here we have sulfur or oxygen here and sulfur here. So sulfur is actually going to be bigger than oxygen. Oxygen is going to be smaller, so we're going to list the oxide. We'll do this one small to big. And then the difference between sulfur and sulfide is gain 2. So if you gain 2, you're bigger, so then you're going to have the sulfur, and then you're going to have the sulfide as the largest. And so that takes care of that. Now, so let's come down here and let's talk real quickly about some ionization energy. We talked about ionization energy in class in that packet the other day, and so this is going to be the energy required to remove an electron from an atom. And we have the first ionization energy, which can be denoted as I1, which is the energy required to remove the first electron from an atom. And we can have successive ionization energies. We can have I1, I2, I3, I4, and so on, and it becomes more and more difficult to remove electrons from atoms as they lose more electrons. And we're going to talk more about that in a table down below. But the greater the ionization energy value, the more difficult it is to remove an electron. And as you try to remove more, the atom becomes more positive, which makes it harder to remove electrons. And that's really what's going on here. Now, we talked about this a little bit in class, but let's talk about it again. We have exceptions to the ionization energy rule. And the exceptions occur in beryllium and boron, as we spoke about in class. Beryllium is to the left of boron. Boron is expected to have a greater ionization energy because boron has more protons, but the truth is that beryllium has a greater ionization energy. And really what's going on here, and this is boron right here, and what's going to happen here is we're going to get a little bit of shielding in that boron molecule, making it easier to remove that 2p1 electron. You get that shielding on the inner that's kind of blocking the positive pull of the nuclear charge or the nucleus from that outside electron, whereas in beryllium, would just be 1s2, 2s2. So to remove one of those s2 orbitals for beryllium, it's going to be more difficult because there's no shielding. There's a little bit of shielding occurring here for the 1s, but not as much as when you have 4 electron shielding. Okay. We also talked about the difference, the exception to the rule in nitrogen versus oxygen. What's expected is that oxygen would be harder or it'd have a greater value for ionization energy, or be harder to remove an electron than nitrogen. But really, what happens is it's harder to remove a nitrogen electron than it is to remove it from an oxygen. And it's due to electron-electron repulsion. So, if we look at oxygen from the standpoint of an orbital diagram, which is a great way to answer this question, if you're given this question on a test, and you will be, on an orbital diagram. your orbital diagram is going to look like this for oxygen. So where you're getting this paired electron here, we call this electron-electron repulsion. And that electron-electron repulsion allows it to have a smaller ionization energy, which means it's easier to remove. And I can't spell easier. Easier to remove an electron from oxygen, even though oxygen is further to the right on the periodic table and it has more protons. Okay. The last thing I want to talk about really quickly here is this ionization energy chart. And so again, these are going to be successive values of her ionization energy for the element sodium through argon. And so you notice this is the first ionization energy here, second, third, fourth, and so on and so forth. From sodium, we see relatively low ionization energy. Sodium, it is not that difficult to give up an electron. But we see a huge jump occur here between the first ionization energy and the second ionization energy. And the reasoning behind that jump is because once you remove an electron from sodium, and I'm going to write sodium's electron configuration. So that's sodium. Once you have removed that one electron from the atom, now you have just noble gas electron configuration. And that means we're trying to remove an electron from what we call an inner shell or a core electron. Now, that's not going to be easy. It's not going to be easy once an atom gets to that noble gas electron configuration. So that's why we see a huge jump in sodium. Now let's go over and look at what magnesium is doing here. And so we have magnesium with a relatively small value. We have 738. And then what's going to happen here is we get a slightly larger value of 1450 kilojoules per mole to remove the second electron off of magnesium, and we expect that. Remember I told you that progressive ionization energies do increase because the atom becomes more positive. But then we see this humongous jump right here. Again, once magnesium, which typically forms a 2+ charge, loses its 2 electrons, it is not going to give up these inner core electrons or the inner shell electrons. So you really have to put a lot of energy in it to try to get that third electron off. So we can use this chart to predict what the ionization energies are going to be as long as we know what the values are or what the charge is. We know aluminum forms a 3+ charge. So then we would expect a large jump at the 4th ionization energy, and so on and so forth. Notice in argon, you have a pretty progressive increase. There's no real huge jumps, and that's because it's already taking a lot of energy to remove an electron from argon, because argon is, as we know, argon is a noble gas, and it has an electron configuration of a noble gas. Okay. Last thing I want to talk about is the sample test question, and they're giving us 2 ionization energies, one for potassium, one for calcium. They're telling us, okay, your first ionization energy is 419, second is 3050, 590, and 1104. And they're saying, explain the difference between calcium and sodium in regard to their first ionization energy. So we would expect calcium to have a greater first ionization energy than potassium, because on the periodic table, potassium and calcium are listed like this, and calcium has one more proton, so we can also say it has a greater nuclear charge. Now, with respect to the second ionization energy, we expect that potassium has a larger second because once it's lost one electron, it now has noble gas electron configuration. Or we could say we're trying to remove core electrons. And once you're trying to remove core electrons, it becomes very difficult, and that's where you get this large jump between the first and second, where in calcium we don't get such a high jump. It doubles, but that's kind of to be expected. That's tonight's homework. There'll also be some book work. Hope you have a nice evening.